All right, so let's take a look at the exercises from 6.2 on volume. So this one really is dealing just with uh, disks and shells. So consider the solid obtained by rotating the region bounded by the given curves. Let's see, y equals square root x minus 1. So that's not even defined when x is less than 1. Square root 0 is sort of like the least valued square root that makes sense among the real numbers, and we're considering functions that output real number values. And so the domain of this function is from 1 and to the right. And actually that shows up in each of the graphs below. Each of the graphs below start at 1. But what's the approximate shape of this function? Well, as you sort of go off to the right, at 2, you'll evaluate to square root 1. At 5, you'll evaluate to square root 4, which is 2. So this function sort of flattens out. At 2, you're up at 1, but at 5, you're only up at 2. So it's really parabolic, but a reflected parabola. I'm guessing it's going to be this guy here, because we're between the function y equals 0. Y equals 0 is just the x-axis, and x equals 7 is this line over here. Yeah, that looks perfect right here. We're between 1 and 7, as it turns out. Because we're revolving about the x-axis, our slices will have no hole in the middle. Will just be pi r squared. So we should just be pi that function squared. So that's pretty straightforward. And I think, yeah, the picture here is going to be this shape that we get down here, because yeah, when we take this guy here and revolve him around, yeah, we get exactly this guy here. Yeah, so that's the situation. Okay, next. Let's see, we're revolving about the y-axis. Now, knowing what we know already about the fact that this section is before we learn the shell method, since we're revolving about the y-axis, we're expecting to be dealing with a function of y. And in fact, we basically have a function of y here, because this x, if you divide by 3, would be able to be isolated, whereas you couldn't isolate the y without a plus or a minus, because you'd be taking square root. So we'd have x equals a third of y squared, which is basically a parabola. X equals 0, which is the vertical axis, and then y equals 6. So let's see, y equals 6. Here's the vertical axis. This looks pretty good. But wait, is that the right shape that we need? Because we need our parabola to be not a standard y equals x parabola or y equals x squared parabola, but rather an x equals y squared parabola. So we need our parabola to be reflected about a 45-degree line, which will indeed give us this picture down here. So just to be clear, this would be a y equals 1/3 x y equals 1/3 x squared parabola, whereas this is our x equals 1/3 y squared parabola. So this is going to be our picture here. And so when we revolve around the y-axis, you can see that our rectangles here will have no hole in the middle, just pi r squared, where the r is the y squared over 3. So not too bad. And when we do the revolution, that kind of feels right there, because that's basically the picture we were looking at. Yeah, that's exactly right. So this has that sort of like undulating shape that we're looking for, whereas this guy here has the inaccurate undulation. Okay, well, there we go. Okay, next, we're between y equals x to the fifth and y equals square root x. So these are both functions of x. I'm expecting we revolve around a horizontal line here, and indeed we do. We revolve around the x-axis. Now, as it turns out, because we're looking between y equals x to the fifth and y equals square root x, which I believe is this region here, we are not touching the x-axis all the way across, and so we will have a hole in the middle. The hole in the middle will be, in fact, the distance from x to the fifth to the horizontal axis. And so, yeah, the graph should have a hole in the middle. And if I'm following our picture, right, so we should be sort of round at the top and round at the bottom. Oh, this is the one here. It's kind of hard to see, my goodness. You really have to zoom in and very carefully look at that shape. But that's definitely the shape that we see up above. And now, as far as the formulation goes for this, the axis of rotation is down here at the x-axis. So the big R is the distance out to square root x, and the little r is the distance out to x to the fifth. And so big R is just square root x minus 0, which is just square root x, and little r is just x to the fifth minus 0, which is x to the fifth. Now, in order to compute the volume of our washer, we've got to use the formula pi big R squared minus pi little r squared, all quantity dx. That would do it, because pi big R squared minus pi little r squared is the area of the surface of our washer, and then dx is the thinness of our washer. If we imagine a rectangle being chopped along the x-axis, remaining from a Riemann sum that's being revolved. So that's that. Moving on to number 4. Oh, this is the one we did in class. So the key thing here is we're revolving about x equals 8. And since we're revolving about x equals 8, that is a vertical line. And so we're going to need to revolve around the vertical line using the techniques that we have had at this point. We're going to need functions of y to do that. And so the functions of y, we're going to have to solve for x equals y squared. So we'll have x equals y squared. That's a parabola shifted on its side. We'll have y equals 0. Let's see, y equals 0 is just a horizontal line. That's the x-axis. And then x equals 4. That's a vertical line. So put this all together. I just want to draw a picture of this so we can sort of imagine this visually. So, right. Y equals square root x. Well, that, as we said, was y squared equals x. And that's a parabola shifted on its side. Y equals 0 is the horizontal axis. Y equals 0. This is x equals y squared. And then x equals 4 is right there. And there's our region. Now, since we're doing a function of, since we're revolving around the line x equals 8 way out here, our rectangle has to be thin with respect to y. When you revolve around, you'll get your washer like so. Boy, that looks rough. Yeah, so this is going to be what? Pi big R squared. The big R is from 8 to the function y squared, x equals y squared. So pi 8 minus y squared minus pi little r squared. Little r is that distance here. That's constant. Those are two parallel lines at minus 8, or excuse me, at 8 and at 4. So that's pi 4 squared. And this is all multiplied by dy. Whoops, I went off the page. Dy, because we're a thin bit of the y-axis is the up and down measure of that washer. So it's a lot to piece together, but hey, we got it all put together, and then we've got a response. What about the next one? The next one also looks like washers by virtue of the fact that we have like our big R squared minus our little r squared. Here we factored out the pi. So the big R squared, well, that means big R is x to the 6th, and the little r squared would be x to the 7th. And so we're between 0 and 1 here. So this, with using set builder notation here, we're between 0 and 1 along the x-axis, because that's where our interval is located. And then our y's are going to be between x to the 7th and x to the 6th, because x to the 7th is this function here that's being squared to get x to the 14th. And yeah, where are we revolving? Well, these are functions of x. We're revolving these around the x-axis so that we revolve around the horizontal line to get the washer that we would need to have this pi big R squared minus pi little r squared structure. A cube is a solid of revolution, not possible, because yeah, the solids of revolution have to be sort of like circular in their nature. You can use integration to find the volume of a cube, but you can't use solids of revolution to do it. Solids of revolution necessarily have to be like objects you could construct on a woodworking lathe or something like this, where a piece of material is spinning radially, and all you can do is adjust the radius of the piece. That's the nature of the beast. When it comes to solids of revolution, we've got disks or washers, or in the next section, cylindrical shells. So it's all circular based. Here, if the region bounded by these curves is revolved on the x-axis, see, this looks like it might be right, but the difference between this formulation, that formulation, is pi big R squared minus pi little r squared, or pi quantity big R minus little r. And let's be very clear here. Can I just write this out? How can I? Where did my snipping tool? I don't know where it went, but let me pull it up one more time. Let me just be very clear. I wanted this is a common misunderstanding, I suppose, by some students, which is that, whoa, what in the world was that? Okay, big R squared, because we have pi big R squared minus pi little r squared, which should equal pi factor out big R squared minus little r squared. And incidentally, all this is multiplied by dx. And so we have a dx at the end. And now here's where we are not equal to. Big R squared minus little r squared is not equal to big R minus little r squared. And why is that? The reason is foiling, because if you were to take this guy here to multiply that out, would not just be the first plus the last, but you'd also have to have inner terms as well. And you'd have a term of minus 2 big R little r showing up, which there's no such term above. So ultimately you have not equal to this guy here. And that's essentially the classic picture that's showing up. If on the other hand, we had pi square root x squared minus pi x squared, well then, yeah, we've had exactly what we need. But as it is, this is false. So I guess false, false in this one. Sweet. Okay, that is our exercise set. I'll stop the video.